Good afternoon, everyone. In this video, I'm going to provide a solution to two problems. The first one is to suggest two different syntheses for the compound shown and to select the one that is preferable and why. First is to do a rheosynthetic analysis. So the compound contains an ester bond. So it is best if we first of all disconnect the CO ester bond to form the two symptoms in the first step. Now the two symptoms are from these two reagents, the carboxylic acid and the alcohol. The two reagents, starting materials, can start together in the presence of an acid. So the lone pair of electrons on the hydroxy group on the carboxylic acid attack the H+ in the acidic medium to give this product. Then the hydroxide also attack the carbon 9 of the intermediate. The process is called an esterification reaction, in which an alcohol and a carboxylic acid react together in a condensation reaction. So water is formed and our target molecule is produced. That is one synthetic route. Another synthetic route that can be used, from the compound we can disconnect the CC bond. If the CC bond is disconnected, these are the two symptoms that will be produced, and then we can have a synthesis. One of the symptoms, the equivalent reagent is an aldehyde. A base, which is a nucleophile, will attack the acidic hydrogen on the aldehyde to form a carbon ion. The carbon ion can now react with the second reagent, which is an alkyl halide, alkyl bromide. So the alkyl bromide will be attacked, since the carbon ion is more basic than the alkyl bromide. So it will attack on that carbon, and bromide will be cleaved in an SN2 reaction. In that case, our target molecule will be formed. If we check, the first route is a little bit more preferable than the second step, the second route, because in the first route here, the reaction is occurring in an acidic medium, is kind of controlled. There is no side reaction that might occur, and water will be synthesized. In this second reaction, in this second route, there might be some kind of reaction elsewhere, because the carbon ion is very basic. It can attack another place, or even it can do some kind of self-reaction, the carbon ion. Now, I provided another route, which I think is also important to mention. The target molecule can be, we can do a rheosynthetic analysis by disconnecting after the ester group, that is the CO ether group, CO ether. So by doing that, we will form a carboxylic acid reagent and also an alkyl bromide. So these two in the synthesis can react because there is a lone pair of electron on the hydroxy of the carboxylic acid. It can actually attack the carbon bearing the bromide, and the bromide will be clipped to form our target molecule. This is also preferable. In fact, even much more preferred than the second route. Alright, for the second question, the second problem, we have to suggest a synthesis route from starting materials with 8 or less carbon atoms and with no stereo center. Looking at the compound, the first thing is to do a retrosynthesis. There can be a disconnection at the CO ester up and down. When the acetal is disconnected, then the first thing is to protect the hydroxy using THP, that is tetrahydropyran, so that there will not be a reaction on the hydroxy group. Then we disconnect at the CO ester bond. After disconnection, then we can do what we call FGI, functional group interconversion. The two hydroxide formed can be converted through some kind of removal of water, dehydration, to form an epoxide. The epoxide itself can also undergo FGI, functional group interconversion, to form an alkene. The alkene can then be disconnected to form our two reagents. So we will form an aldehyde and an alkyl bromide. The aldehyde should not be mistaken to be a benzaldehyde, because the compound, the ring is not a benzene ring. It only contains two double bonds. We should take note of that. Now for the synthesis, the two reagents that are formed here can actually react the aldehyde and the first reagent is the alkyl bromide, the protected alcohol. The protected alcohol will be deprotected here actually. Now after the protection, it's a reagent for us. So for the synthesis, the alcohol having bromide here will be first of all protected using THP. After it has been protected, then we can now react it with the aldehyde. The aldehyde contains an acidic hydrogen, a base or a nucleophile. We remove the acidic hydrogen to form a carbon ion. The carbon ion can actually attack the carbon bearing the bromide to form a C bond. The product formed, which contains a ketone, can then be reduced to form an alcohol selectively. So the alcohol will be formed because the first The hydroxide has been protected, so it will not be reduced in this step. So it is only the ketone that will be reduced to a secondary alcohol. Now, the next step is to form an epoxide. Epoxide will be formed on the alcohol. In this way, we choose partially butanoic acid because we want to form a stereo. We want it to attack at the top, so that we have the epoxide will be formed at the top. Now, so the next thing is to do hydration to react it with water in the presence of an acid. So we formed dihydroxides. The water can attack from below. The water will attack from below, then we will form a stereo center here. So we have actually formed a compound with stereo centers, in which we did not start with stereo center. After that is formed, the next thing is to react it with an acyl chloride to form the acetal. We have to acetylate it. So if we acetylate twice, the two hydroxide will be acetylated. After the acetylation, we cannot protect the protected hydroxide using water in the presence of an acid. So we form our target molecule. Thank you.